Hello and welcome to this FP2 exam paper walkthrough. This was the June 2022 paper. You were allowed an hour and a half, a calculator and the formula booklet. Jumping straight into question 1. Given that this is true, determine the value of A and the value of B. So we're just doing partial fractions here. We've already been given what it should be, so let me jump straight to the next line where we cross multiply by the denominators on this side, effectively having multiplied everything by the denominator on the left. Now if we let n equal -1, then the a bit will become 0, and the left hand side we get -2 plus 1, -1. This is 0, that's why we do that. And then -1 squared is a 1, so b is equal to -1. Then I let n equal 0 so that the b term becomes 0. On the left hand side we get 1, and we get 1 squared, so that's just a, and 0 here, so a is equal to 1. So we can say that 2n plus 1 over n squared, n plus 1 all squared, is equal to 1 over n squared minus 1 over n plus 1 squared. Double check. Yes. Hence, show that for n is greater than or equal to 5, this is true. So we're going to be using the method of differences here, where a, b, and c are integers. So I can check that at the end that they are integers. So let's go for this, part B. We are doing the sum, r is equal to 5 to n, 2r plus 1 over r squared, r plus 1 all squared. So that's the same expression, but with an r instead of an n. Now I have to keep in mind here we're starting at 5. That's quite a big number to start with. Usually we start at 1 or 2. So that's a 1 over 5 squared minus 1 over 6 squared. And given that we've got n squared and n plus 1 squared, I think this is a fairly straightforward one. We're not going to need too many rows to see what's going on here. We can already see that this and this are going to cancel. So there's the pattern. So let's jump, do a dot, 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 and then jump to r is equal to n minus 1. And then finish with r is equal to n. So we can see that these two cancel, this one cancels with what's in the dot dot dot, so does this one, and we're left with just the first term, 1 over 25, and the last term, 1 over n plus 1 squared. What format do they want? We need to put it all together. So let's combine these two fractions here. So n plus 1 all squared minus 25 over 25 n plus 1 squared. So that gives us n squared plus 2n plus 1 minus 25, 25n plus 1 squared, n squared plus 2n minus 24, 25n plus 1 squared. Now I think that will factorize, but at the same time I don't think they wanted it factorized, no. So a is the n coefficient, b is the constant, and c is in the denominator. So a is 2, b is minus 24, and c is 25. Question 1 finished. On to question 2. This says, use algebra to determine the set of values of x for which this inequality is true. Okay, those two first words, use algebra, means I can't start by sketching the graphs. I need to do some algebra. That's all it is asking. So let's multiply both sides by the denominator squared. So I've got x minus 5 times x plus 3 squared is greater than 9x plus 3 squared over x plus 3. The reason for squaring that is so that we can be sure it's a positive number. We don't need to worry about the inequality sign changing. We can cancel those two and bring the 9x plus 3 in its bracket onto the left. Dear, don't forget that bracket. That was untrue without the bracket. X plus 3 squared minus 9 lots of x plus 3. And then I've done that without expanding first because I could see that x plus 3 will be a factor of those two. So then we get x minus 5 times x plus 3 minus 9. Now I can expand this to give x squared minus 5 plus 3 is minus 2x minus 15 minus 9. That's minus 24. That's very similar to the numbers we had on the previous question. So that also will factorize. Got a 6 and a 4. We want minus 6 plus 4. So our critical values are minus 3, 6, and minus 4. If I sketch this out, 6, minus 3, minus 4, and if I expand just the x terms, I can see it's a positive cubic, which is going to look like that. So if I match this over here, not worrying too much about it because it's just giving me an idea of where it's above and below the x-axis, then we can say that this thing is less than 0 when x is less than minus 4, and when x is between minus 3 and 6. That is my solution to part A. Part B, hence or otherwise. So here it's giving you the choice. If you see the word hence and not the phrase or otherwise, you must use what you've just done to help with the next part. But this or otherwise is giving you a completely separate option. It's saying you can use what you've done in part A, or you can do any other method at all. You don't need to use part A. So here you could just start all over again if you wanted to. And to be honest, usually I probably would. But let's try and do a different method. Let's do a graph. So if I try and sketch this out on a graph, I should be able to see where the line x minus 5 is less than 9 over x plus 3. Of course, to do this, I need to be able to sketch both of those. So we've got x minus 5 is less than 9 over, was it minus? No, plus 3 in a modulus. This is part B. So as I sketch these out, I'm just going to logic my way through it, as it were. Got y there, x here. X minus 5, that's pretty easy. That's a straight line graph. Gradient 1 going through minus 5 and 5. Now the other graph, if I do a sneaky sketch up here of 9 over x plus 3 without the modulus, that has an asymptote at minus 3, because if you try and put minus 3 in there, you'll be dividing by 0, so it can't cross that line. And then it's a 1 over x style, so it kind of looks something like this. And I can check as well that the x-axis must be an asymptote, because I can't ever get a 0 out of this fraction. You can't divide 9 by anything that will give you a 0. You can get closer and closer to it as the divisor gets bigger and bigger, but you can't actually get to 0. So that's how that looks. However, if I put a modulus on there, then this bit here on the bottom reflects up here like this. So what I've got is the asymptote still at minus 3, and then a graph that comes down like this and down like this. And the question is, when is the line less than the curve, or lower down than the curve? That is at this point here, and everywhere to the left of that point. So if I just jump back up here, I can be pretty sure that that point of intersection is a 6 from our previous work. So when x is less than 6, then this line is less than the curve. However, there's one extra little bit here because the asymptote is a point where the curve cannot exist. That means the curve is not greater than the line at that point because there is no curve at that point. So we need to put on a little x cannot equal -3 caveat onto that. And that is question 2 finished. On to question 3. The transformation t from the z-plane to the w-plane is given by this transformation here. The circle with the equation modulus of z equals 3 is mapped by t onto another circle, C. Determine a Cartesian equation of C. Okay, we've got two parts to this question, but I imagine the bulk of the marks come in part 1, because by the time we've got that equation, the centre and the radius of C should be pretty easy to find. So let's go through the usual process. We want to start by rearranging this to give z as the subject. So we'll have zw plus 4iw equals z. 4iw is equal to z minus zw, z1 minus w, 4iw over 1 minus w equals z. Now we put it into the modulus that we've been given. Modulus of this, 4iw over 1 minus w must equal 3. Now I'm going to split my modulus, I think, 4iw over 1 minus w equals 3, and then I can multiply by that. And now I want to get rid of the modulus signs, so I want to square everything. But before I do that, I want to know what is the real part and what is the imaginary part. So I need to allow that w has both of those inside and change that into u plus vi. So we've got 4i times u plus vi is equal to 3, 1 minus u plus vi. And then we've got 4iu minus 4v, because the I squared becomes a minus 1. And then we've got 1 minus u minus vi. So 1 minus u, if I just put that in brackets, that's the real part. And then minus vi is our imaginary part. Now I can get rid of my modulus signs by squaring everything. And that's the real part squared plus the imaginary part squared. So here we've got minus 4v squared, that's 16v squared, plus the imaginary part, that's 4u squared, so that's 16u squared. Now don't forget the 3, that also squares into a 9, and then we've got the real part squared over here, plus the imaginary part squared as well. So straight away I'll multiply all of this out on the right. So we've got 1 minus 2u plus u squared, but times everything by 9 as well. So we've got 9 minus 18u plus 9u squared plus 9v squared is 16v squared plus 16u squared. Now I'm just rearranging. We're going to complete the square and get it into a format where we can recognize the equation of a circle. So we've got 16v squared minus 9v squared is 7v squared. Same with the u's, 7u squared plus 18u minus 9 equals 0. So if I divide everything by 7 to get these to have a coefficient of 1, then we've got 18 over 7u minus 9 over 7. Complete the square. V squared is already kind of done. U squared is u plus 9 over 7 all squared. Now I need to subtract 9 squared over 7 squared, and we also still need the 9 over 7 that was already there to make all of that consistent with what came before. So bringing those constants onto the right hand side, they combine to give 144 over 49, which is looking very nice. U plus 9 over 7 squared, v squared. So that is the equation of a circle, and part II wanted us to state the center and radius, which we can do now from that equation. So that's part I, and then I. The centre is minus 9 over 7, 0, and the radius is 12 over 7, the square root of the right hand side. That was a fairly standard transformation question. That was quite nice. On to question 4. Determine the general solution of the differential equation this, giving our answer in the form y equals a function of x. So to do this, let's recognize it is of the form this. So the first thing to do is to find an integrating factor, e to the integral p of x dx, which gives us e to the integral of minus 3 tan x dx, which I'll write like this. And the integral of tan is here in your formula booklet if you need that. It's the natural log of secant x. So that gives us e to the minus 3 natural log secant x, and the minus 3 can become a power. The e and the natural log cancel out to give us secant to the minus 3x, and that is equal to cosine cubed x. So this is our integrating factor. So we've done all of that in order to get something to multiply our original equation by. So dy by dx minus 3y tan x is equal to e to the 4x, leaving space there for a reason, times secant cubed x, and the whole point of this was to multiply this equation by that integrating factor. So we've got cos cubed x here, cos cubed x here, cos cubed x here, which is nice because they immediately cancel. And the whole point of doing that is because the left-hand side we can now say is the derivative of y times that integrating factor. So cos cubed x times y is equal to the integral of e to the 4x dx. Now on the surface of it that might look a little bit strange, because how do you get a tan x by differentiating a cos? But what they've done there is you differentiate that, you get cos squared and the sine, and then if you put an extra cosine in by doing cos divided by cos, you can make a cos cubed again, and the sine and the cos make a tan, if that makes sense to you. So all we need to do is integrate this right hand side, which gives us 1 over 4 e to the 4x plus c. Don't forget the plus c at this point, that's important. And we need it in the form y equals. So we've got 1 over 4 e to the 4x times secant cubed, or divided by cos cubed, however you want to write that, plus c times secant cubed x, like so. So that's the solution, the general solution. Now the particular solution, x equals 0, y equals 4. So as usual, we just put that in and find the constant c. So 4 is equal to e to the 4x when x is 0 is a 1, so that's 1 over 4. Secant x when x is 0, that's a 1 as well, so that's plus c. So c is equal to 15 over 4. So our final solution, particular solution, is 1 over 4 e to the 4x times secant cubed x plus 15 over 4 secant cubed x. Double check that's finished. Yes. On to question 5. That's question 5. Okay. Given that this is true, so this is the second derivative, determine the third derivative in terms of the second, the first, and the original y. So we're just going to take what they've given us, and differentiate it again. If I write this out, okay, here we go. We need the product rule in this first term, so I'm going to differentiate y, that gives dy by dx, and leave this alone. Then I need to leave this alone and differentiate the second derivative, which gives us the third derivative like that. Now this, I'm going to bring that 2 down, that's a 4 times this bracket to the power of 1 multiplied by what's inside the bracket, the derivative of that. So we've got a second derivative here using the chain rule. You could also write that as dy by dx times dy by dx and apply the product rule. You'd get the same answer if you simplified. Then here we've got 2 dy by dx. And all of that is equal to 0. Now the way the question is phrased makes me think we should rearrange this to get d3y by dx cubed by itself. So if I first write it like this, isolate this term, we get 2 dy by dx, and then these terms are actually the same. We've got 4 of these and 1 there, so there's 5 of them, so we've got minus 5 lots of dy by dx times the second derivative. And then I need to divide by this y, so let me just be a bit cheeky there and do that. So that's our third derivative. Now, given that y equals 2 and dy by dx equals 1 at x equals 0, so these are all true at the same time. Y equals 2, x equals 0, and the first derivative is 1. Determine a series solution for y in ascending powers of x up to and including the term in x cubed. Now I want to show you the formula booklet here because the last paper I did I was using the wrong booklet. So this is an international paper. So in the international formula booklet you have the one that we need, f of x, that's given in these terms in the formula booklet for the UK as well. But what's not given in the formula booklet for the UK is this one here, which I've used in a previous video. This is in the international formula booklet. So take note of that if you need that one in your exam. It is in the booklet for the international papers. But for today, this paper, we need that top one, so I'll just copy that across. F of x is equal to f of naught plus x times the first derivative evaluated at naught plus x squared times the second derivative evaluated at naught divided by 2 factorial plus x cubed divided by 3 factorial. And we need, yes, x cubed. So f of x, the function itself, that's y, so that's 2, plus x times the first derivative, we've been told is a 1. And then the second derivative I haven't evaluated yet, so the second derivative is the one we started with in the question. I'll use the one that I wrote down at the top of the screen here. So we've got y, which is 2, times the second derivative, which is what we want, plus 2 lots of the first derivative squared minus 2 lots of y equals 0. So that's a 4 minus a 2 is a 2 divided by 2 is a 1. And then we're also going to need the third derivative, which is what we found at the top of the screen here, using the information we've got so far. So the third derivative is equal to 2 over y, which is 2, times the first derivative, a 1, minus 5 over y times the first derivative times the second derivative squared. So that's 2 over 2 minus 5 over 2 minus 3 over 2. Okay, going back down to our expansion, this is x squared times a 1 divided by 2 factorial is 2, plus x cubed times minus 3 over 2 divided by 3 factorial, which is 6. Simplifying all of this, we've got 2 plus x plus a half x squared minus a quarter x cubed plus dot dot dot. Double checking that we've finished. Yes. Question 5 done. Question 6, polar coordinates. The curve shown in figure 1 has polar equation this, from 0 to pi, not including pi. A is a positive constant. The tangent to the curve at the point A is parallel to the initial line. Probably will need that. That's dy by d theta equals 0 to find that point. And yes, I've done this before, saying something like that and then immediately seeing that it is. Part A show that the polar coordinates of A are this. So this is exactly what we're going to do. And y is equal to r sine theta as a general statement for polar coordinates. In this particular case, we know that r is 4a1 plus cos theta, given in the question, times sine theta. And then we're going to need to differentiate this, so I will just expand this out. We've got 4a sine theta plus 4a sine theta cos theta. And then differentiating this with respect to theta, 4a cos theta. Then we can use the product rule here. Differentiate the sine gives us a cosine, and we leave the cosine alone, so we get 2 of those. And then we leave the sine alone, and we differentiate cosine, which gives us minus sine, so that becomes a minus sine squared. Now this has to equal 0, so if I change my sine squared into a cos squared, we can use a quadratic formula. So first of all, let's remember that a is a positive constant, so at this point I can divide everything by 4a. So we've got cos theta, and put on there a is greater than 0, therefore cos theta plus cos squared theta minus 1 minus cos squared theta is equal to 0, so that gives us 2 cos squared theta plus cos theta minus 1 equals 0. Can I factorize that? I think maybe. 2 cos theta, and then the cos theta, and then we want a positive cos theta, so if we make that a plus 1, that's a minus 1, that should work. So either 2 cos theta equals 1, or cos theta equals minus 1. Now if cos theta equals minus 1, then theta equals pi, but we had a limit, and the limit said no pi. So this is not one of the solutions. This is outside the domain. And if you look at the graph, it's obviously not the point A. And the other option, cos theta is equal to a half, gives theta as pi by 3. Is that what we were expecting? Yes. Now r is equal to 4a1 plus cos theta. And we've just said that cos theta is a half. So that's 1 plus a half. 3 over 2 times 4 is 6a as expected. So point A is 6a pi by 3. So we've got point A, the coordinates of that. Now the point B lies on the curve such that the angle AOB is pi by 6. So if I draw OB on here, AOB is pi by 6. Okay, and we've just found that the angle from the initial line to A is pi by 3, so all of this angle here is pi by 3, which means this one is also pi by 6. So B is at theta equals pi by 6, and A is at theta equals pi by 3. The finite region R, shown shaded in figure 1, is bounded by the line AB and the curve. Use calculus to determine the area, giving an answer in this form where n, p, and q are integers. Okay, so our approach here, we're going to integrate the curve from this angle to this angle, and that will give us all of that region in between OB and OA, and then we can use the trigonometric area of a triangle, half AB sine C, because we know that angle in here, and we can figure out the length OB, so I'll need to know what is R at this point. I already know R here is 6A, so we can find the area of the triangle AOB and subtract it from the integral of R squared, or half R squared d theta, minus the area of the triangle, and that will give us the area of R. We're going from pi by 6 to pi by 3. So I hope that quick outline of what we're going to do is clear. I'm going to do them as two parts, and then I'll put them together for R at the end. So we've got a half, that's part B, a half R squared d theta from theta equals pi by 6 to theta equals pi by 3. And that is a half times the integral of, we've got R on the screen there, so that's 16a squared, 1 plus cos theta squared. So I know a is a positive constant, I can take that and the 16 outside, divided by the 2, we've got 8a squared, and then we've got 1 plus 2 cos theta plus cos squared theta d theta. And immediately I think to myself, I don't like that cos squared because that's going to be awkward to integrate. Let's change that using the double angle formula. So I'm going to change that cos squared into a half plus a half cos 2 theta. So we've got 8a squared integral 1 plus 2 cos theta plus a half cos 2 theta d theta. And can I take some things out? That's a 3 over 2. So let me take the half out. Let's make that 4a squared integral 3 plus 4 cos theta plus cos 2 theta. So I've combined my constants and factorized out a half. Now we're ready to integrate. And we've got 3 theta plus 4 sine theta plus a half sine 2 theta. Oh, and I've been very lazy with my limits here. That should be pi by 6, pi by 3. Oh, usually I like to write them all out. Never mind, let's jump down to here. So we've got 4a squared, and then we've got 3 times pi by 3, that's pi. Sine of pi by 3 is root 3 over 2 times the 4, that's 2 root 3, plus a half times sine 2 pi by 3. So that's a root 3 over 2 as well. So that's root 3 over 4. Pi by 6 times 3, pi by 2. Sine of pi by 6 is a half, so that's 2. And a half sine of pi by 3, we've already said that's root 3 over 2, so that is also root 3 over 4. Tidying this up a little bit, we've still got the 4a squared there. Pi minus pi by 2 is pi by 2. We've got 2 root 3, well the root 3 over 4 cancels, so that's just 2 root 3. And then minus 2. Expanding this out, it gives us 2a squared pi plus 8 root 3 minus 8a squared. Now remember, that's the integral, so that's all of the area between OB and OA. Now we need to subtract the area of the triangle, a half AB sine C. I haven't even figured out what R is for OB yet, so let me do that now. That's 4a times 1 plus cosine of theta, which we said was pi by 6. That's 4a 1 plus root 3 over 2, not the nicest. Let's combine those. So that's 4a 2 plus root 3 over 2. And then I can cancel that. 2a 2 plus root 3. So a times b times sine c, I need this times this divided by 2 times the sine of pi by 6. So 6a times 2a 2 plus root 3 6a times 2a 2 plus root 3 times the sine of the angle between them, pi by 6, which we know is a half. So let's cancel those. 6a squared times 2 plus root 3 times a half. So that cancels down to 3a squared 2 plus root 3. That's 6a squared plus 3a squared root 3. So r is equal to the integral solution that we've got at the top of the screen there, 2a squared pi plus 8 root 3. Hang on a minute, that should have an a squared in there somewhere. Squeeze that in there. 8a squared root 3. That's better. Minus 8a squared, and all of this is being subtracted by the triangle area 6a squared plus 3a squared root 3. So we've still got our pi term. That doesn't change, 2a squared pi. Now we've got 8a squared root 3 minus 3, so that's 5a squared root 3 minus 8 minus 6 minus 14a squared. Now what's our format? We want a squared in front, and then all of these should be integers. Yes, it's looking good. A squared 2 pi plus 5 root 3 minus 14. And what were our letters? Oops. N, P, Q. So N is 2, P is 5, Q is minus 14. On to the next question. Question 7. Show that the transformation y equals xv transforms this equation into the much simpler equation with v and x. So let's start this one with y equals xv, and because we need dy by dx's changing into dv by dx's, I'm just going to differentiate this. Using the product rule, I get dy by dx is equal to x, differentiate that, you just get 1, so that's v, plus leave the x alone and differentiate v with respect to x, dv by dx. So that's our first one already done. We can substitute that in here. But we are also going to need the second derivative, so let's do it again. Differentiate v with respect to x, and then we need the product rule again. X is just a 1, so we've got dv by dx plus x times the derivative, so that's the second derivative now, like so. Then of course we can add these two together, and this is the result for our second derivative y with respect to x. Now we're ready to substitute in. We're going to need to substitute the first, the second derivative, and also y equals xv. So there's quite a lot of substituting going on here. Let me write this out here and drag it down. y and x squared. Apologies for the poor handwriting there. Let's substitute in. We've got 3 times the second derivative, so that's 2 dv by dx plus x d2v by dx squared minus 6 over x times the first derivative was v plus x dv by dx, plus 6 over x squared times y. Y at the top of the screen is our original transformation, y equals xv. So we've got this, plus 3 lots of y, so that's another xv there, equals x squared. Now we need a lot of this to simplify down, so let's start expanding these brackets. We've got 6 dv by dx plus 3x second derivative minus 6v over x minus 6, the x's cancel there, dv by dx, that's good, that will now cancel with that, plus 6x, oh no, that x is going to cancel as well, so that's v over x, that's good, that will now cancel with that, plus 3xv equals x squared. We've got 3x d2v by dx squared plus 3xv equals x squared, and the format we want to keep the 3's and we want to cancel one of the x's. So we've got 3 d2v by dx squared plus 3v equals x as required. Hence, obtain the general solution of the differential equation 1. Often they split this into two parts. They get you to do the general solution of equation 2, and then part C, they say, okay, now find the general solution of part 1. We want to do all of that in one question here, giving our answer in the form y equals a function of x. So we need to solve this, then transform it back in one question. So to solve this, we are going to do it in the usual way. We need the complementary function and the particular integral. So let's start 3m squared plus 3 is equal to 0. That gives us minus 3 over 3 for m squared. So m is equal to I, the square root of minus 1. Then you need to be able to recall what that means for the complementary function. The form here, v is equal to e to the px, but that's the real number, and the real number here is 0. And then it's a cosine x plus b sine x, because the imaginary part there is just a 1. That's the complementary function. Now the particular integral, the right hand side of this is an x, so try a general linear function. So let's try v is equal to lambda x plus mu, dv by dx then is equal to lambda. Second derivative is 0, which is nice because we don't have a first derivative, and the second derivative is 0, just gives us 3 lots of v equals x. So 3 lots of lambda x plus mu. Oh, maybe I should make it clear that I've got a 0 here. That has to equal x. So 3 lambda x plus 3 mu equals x. Equating the coefficients, we can see immediately mu must equal 0 and lambda must equal 1/3. So v is equal to 1/3 of x is our particular integral. So the general solution, putting these two together, v is equal to a cos x plus b sine x plus 1/3 of x. Now remember, this is equation 2 that we've solved. We want the solution to equation 1, so we need to go back to the transformation that we had originally, y is equal to xv, and transform it back. So y is equal to xv gives v is equal to y over x. So we change this v into y over x. A cos x plus b sine x plus 1/3 of x. Multiply everything by x to get y ax cos x plus bx sine x plus 1/3 of x squared. And that is the general solution for equation 1. That was part B. So that's the question finished. On to question 8. The Moivre's theorem. Using the Moivre's theorem, show that sine 5 theta is equal to this. Okay, this is a fairly standard approach. We need, when r is equal to 1, we've got cos theta plus I sine theta to the power 5 is equal to cos 5 theta plus I sine of 5 theta. We'll expand the left-hand side out with the binomial theorem, and we'll equate the imaginary parts because we want sine instead of cosine. As I've done on previous videos, for the binomial theorem bit here, I'll just use C and S to make it a little bit quicker and fit it all on one line. So we've got cos power 5 plus 5 cos power 4 I sine plus 10 cos cubed I squared sine squared plus 10 cos squared I cubed sine cubed plus 5 cos I4 sine 4 plus I to the power 5 sine to the power 5. Oops. Let's be consistent. There we go. Now I need the imaginary terms only. So equating imaginary terms, we get sine 5 theta from the right hand side of the original equation here is equal to all of the imaginary terms from the left hand side of the original equation, which is the right hand side of this bit. So we're going to need this one, 5 cos power 4 theta times sine theta. That was an imaginary term. This is not, because the I squared becomes a minus 1. This is, 2 of these become a minus 1, and we're left with 1 there. So we've got minus 10 cos squared theta sine cubed theta. This one is not imaginary, and obviously this one isn't either. And this one is, I power 4 is a 1, so we've just got plus sine power 5 theta there. Now we need it in powers of sine, so our cosines here we're going to have to change using cos squared theta is equal to 1 minus sine squared theta, and we're also going to need a power 4, so if we square that we get 1 minus 2 sine squared theta plus sine power 4 theta, and substitute that in here and this one in here. So sine 5 theta is equal to 5 lots of 1 minus 2 sine squared theta plus sine power 4 theta times sine theta minus 10 lots of 1 minus sine squared theta times sine cubed theta plus sine power 5 theta. Expand it all out, collect it all together, and hopefully it's what we need. So we've got 5 sine theta minus 10 sine cubed theta plus 5 sine power 5 theta minus 10 sine cubed theta plus 10 sine power 5 theta plus sine power 5 theta. So we've got 10, 11, 16 of these, and then minus 10, that's minus 20 of these, and 5 sine thetas. So we've got 16 minus 25. Yes. Great. That's part A finished. Part B, hence determine the 5 distinct solutions of this equation here. We've got 16x power 5 minus 20x cubed plus 5x. That matches, but then we've got a plus 1 over 5 equals 0. So part B, 16x power 5 minus 20x cubed plus 5x plus 1 over 5 equals 0. let x equal sine theta. Now we're using the part just at the top of the screen there. Oh no, we're not just yet. Let's substitute in first. 16 sine power 5 theta, getting ahead of myself there. 20 sine cubed theta plus 5 sine theta plus 1 over 5 equals 0. Now we're using that bit at the top of the screen to change these first three terms into sine 5 theta. And we can rearrange this to give 5 theta is equal to the inverse sine of minus 1/5. That's not a very nice answer. What do we need? 3 decimal places. So my first answer, let's have theta 1 is equal to 1/5 of the inverse sine of minus 1 over 5. That's minus 0.04027 ... And because these are horrible decimals, I don't want to have to come back to convert them, so I'll do them one by one. X is equal to the sine of theta. So that, perhaps unsurprisingly, gives me minus 0.040 to 3 decimal places. Because when theta is very small, sine of theta approximates theta. Second answer, if I just add 2 pi to that and then divide by 5, 1.2163 ... And that gives me 0.938 to 3 significant figures. No, 3 decimal places. Well, yes, 3 significant figures as well, but that's not what I meant to say. Next one, 2.4730 ... giving the answer 0.620, 3 decimal places. I'm not going to get them all on this line. Do theta 5 down here. 3.7296 minus 0.555, 4.9862. So the final x value is minus 0.963. And if I do one more to check, it brings me back to minus 0.040, which I've already got. So these are the 5 distinct solutions to the equation. Oh, there's a part C. Oh, I thought that was it. Use the identity given in part A. Oh, we've gone back to integration. Okay, so we are using the identity to integrate this, which is not quite the same. Okay, let me copy this out. 4 sine power 5 minus 5 sine cubed minus 6 sine theta d theta, integrating from 0 pi by 4. This is part C, and our identity, let me drag this down as well. Okay, this is the information we've got, but you can see that they don't match. So let's have 1/4 of this. So that will give 4 sine power 5 of theta minus 5 sine cubed of theta plus 5 over 4 sine of theta. Now that still doesn't match, but we are mostly there. To get our plus 5 over 4 sine theta into a minus 6 sine theta, I need to subtract 29 over 4 sine theta. So 1/4 of this minus 29 over 4 sine theta is equal to 4 sine power 5 theta minus 5 sine cubed theta minus 6 sine theta, and that does match. So the integral becomes the integral from 0 to pi by 4 of 1/4 sine 5 theta minus 29 over 4 sine theta d theta. And while that's not as nice as I thought it might be, it's certainly better than it was. We can at least integrate this. So if I just take that quarter out, I don't like fractions in my integration. Although there is a danger of forgetting the quarter is in the front there. So sometimes I put them in. Don't need that 1 there anymore either. So we've got 1/4 sine 5 theta is minus 1 over 5 cosine 5 theta, and plus 29 cosine theta from 0 to pi by 4. Now we go ahead and put in our limits. That gives us minus 1 over 5 times cosine 5 pi by 4 minus root 2 over 2 plus 29 lots of cosine pi by 4, which is root 2 over 2, minus cosine 0 is a 1, so that's minus a fifth plus 29. That gives us 1/4 of 73 over 5 root 2. That does not look very nice. Minus 144 over 5. And what do we need the format to be? A root 2 plus b, where they are rational numbers. Okay, that makes me feel a bit better. Root 2 and a constant. So let's put the quarter in, and we get 73 over 20 root 2 minus 144 over 20. And that is 36 over 5. Now it was A and B, was it? A and B. So A is the rather horrible 73 over 20, and B is the slightly nicer 36 over 5. And that is the end of the paper. So once again, I hope that that has been helpful for you, and maybe I'll see you in another video.